All right, welcome to today's lecture. So we're going to be going over vertical oscillations and pendulums. This is going to be a shorter lecture than normal. It's just going to be 2 videos. The reason for this is I don't want to get into a brand new topic, and there's nothing else within the chapter I really want to cover in this class. You will probably see most of the rest of chapter 15 in your Physics 130 class. I know some professors, for example, don't cover the physical pendulum. I didn't when I did 130 last year. So it's just kind of going to depend on, kind of what that ends up, who you end up taking for Physics 130. So let's go ahead and recap last time. So we focused on this thing called simple harmonic motion. And we had these equations. So we looked at our position. It is a function of time. We had a couple different equations for omega, sine or cosine, and the amplitude. Now in the worksheet you played with a couple of different situations where you had to choose sine or cosine and whether we had a positive or negative amplitude to start with. And so if this is our starting equation though, we do need to take the derivative to get the velocity or the acceleration, because with these we have a non-constant acceleration, therefore we cannot use kinematics. And when we looked at simple harmonic motion, we had a box on a spring that was horizontal. And everything we've dealt with so far has assumed that we have a horizontal box on a spring, and it was friction-free. When you revisit this topic in Physics 130, you might introduce friction, and then you'll have another term attached to your position as a function of time. But we're not going to be getting into that. But first, what we want to do is we want to look at some more ways in which we can observe simple harmonic motion, because a box on a spring is not the only way. So in this first video, we are going to be looking at vertical oscillations. So instead of our box being horizontally moving back and forth, we're now going to be moving up and down. And this is what the lab is going to look like this week, as we are going to be using a vertical oscillator. So we need to see if we need to treat that any differently before you can do the math for the lab. In the second video, we are going to be discussing the simple pendulum in particular, not just pendulums in general. So we're going to have a couple of conditions that we put on our pendulum in order to go through and utilize it. So the reason we need to talk about vertical oscillations is it turns out it's a lot easier to set up. It's a lot easier to do demonstrations with a vertical oscillator compared to a horizontal one. And so because of that, and because if we think about where you will see a spring in your day-to-day life, if it's oscillating, it's probably in the vertical direction, which means we have to consider some different stuff. So we need to make sure we know how to use vertical oscillators in comparison to horizontal ones. So we are now moving in the direction of gravity. Right? Gravity, we've established, moves in up and down, or really just the downward direction, which we've really been commonly just using as the y direction. If we're now moving in that y direction, well, as the, whatever's on the spring, as it moves downward, it should accelerate because of gravity. And it's going to slow down as it goes against gravity. But we also have the spring. And the spring, the force points in the opposite direction of motion. So these two forces, are they helping each other? Are they hindering each other? That's what we need to figure out. Because if gravity is changing how our object moves, well, that means that maybe we need a different equation for our position as a function of time. And that's what we want to explore. Do we need to treat these vertical oscillators differently because they are moving in the direction of gravity? So here we have an unstretched spring attached to some sort of ceiling. And this is going to be its equilibrium length. This is what the spring would be like if nothing is attached to it. It's not stretched, it's not compressed. When we add some mass to our spring, it is going to result in the spring stretching. So here, we want to make sure that we are using the same notation that we used when we stretched the spring previously. So even though this is down, we want to call it positive because the spring is stretched. And that means that if the spring was compressed, that would result in a negative value, even though that's going to be an upward direction. So again, we need to remember that we get to choose our coordinate systems. And so if we want to match stretching and compressing for the horizontal spring to the vertical spring, we will need to flip the y direction for us. Now let's just assume we've placed this box here. It has some mass m, and we're going to let it sit at its new equilibrium length. So this length here, even though the spring is stretched from its original value, it is stretched to a new equilibrium length. This is the equilibrium length of the box with the spring. And it's going to be different by some amount of length. And on the right here, we have the free body diagram for our mass. Again, the spring's going to want to pull upwards. It wants to go back to its unstretched value, whereas the force due to gravity is pointing downwards because gravity is an attractive force between an object and the earth. So, oops, that should be shifted, not sifted. Which is so we've shifted equilibrium. This dashed line here tells us if there was no box on the spring, this is where our height would be. But because we have this box on the spring, the bottom of our spring has moved some length delta L. So if we want to go through and calculate what this delta L value is, we need to consider the two forces we have acting on our box. We have the force due to gravity and the force due to the spring, which we can calculate using Hooke's law. So for Hooke's law, it's going to be negative kx, whereas gravity is going to be mg. So here we are assuming that the proof in the textbook goes through and assumes that up is positive y, down is negative y. Because this is going to be where we are at equilibrium, so we're using Newton's first law, if we flip our coordinate system such that negative y is positive downwards, we're going to end up getting the same exact value. It's as if we've multiplied both sides by -1. -1 times 0 is going to be equal to 0. So the textbook, when it goes through the examples, again, coordinate system and making sure you draw that coordinate system is important. Textbook, I believe, does I think for the examples, it does use positive y as upward. So that means compressed and stretched are in opposite directions. So when you're deciding when to do these questions, choose a coordinate system. So we've replaced the, Hooke's law, so negative kx, it's positive, so it's k delta L. Force due to gravity is negative, it's mg. So we just want to rearrange to solve for the equilibrium length, so that delta L. So delta L is just going to be mg divided by k. So that change in our equilibrium position is going to be related to the mass of our object, the acceleration due to gravity. So if you're on Earth versus the moon versus Pluto, those values are going to be different. And it's inversely related to the spring stiffness constant. So it turns out that when we have a vertical oscillator we technically never have an unstretched spring. So even when we are at our maximum compressed value, it's still stretched from the original value. So here, if we look at the coordinate system that the textbook has put in the middle, again, it's saying that the textbook makes it so that A is positive in the vertical direction and negative in the negative, so the downward direction. You are welcome to flip this. Personally, I prefer to flip this. So when I'm going to do an example, I'm going to flip my coordinate system because I'm an adult and I get to choose that. I like it when compressed means the same in vertical and horizontal oscillators. That is my personal preference. You are welcome to follow the textbook if you want to. You're an adult. You get to make that decision. So regardless of what amplitude we're at, or if we're at the equilibrium position, we have stretched the spring from its original position without the mass. So the spring is always going to be stretched. If we continue looking at our image on the right, this leftmost part is what we saw on the previous slide when we just attached the mass to the spring. On the right here, we have now started motion. We've let go of the spring and it's moved sometime, and here it's between the compressed amplitude and our equilibrium position. And if we look at the free body diagram, the force due to gravity is larger than the spring force. So that tells us that our net force is going to be in the downward direction, which means the acceleration is in the downward direction. Because our spring force is pointing up, we can assume that we are slowing down while moving upwards. So our new for this particular box, based on its current location between maximum compression and equilibrium, our spring force can be given by negative K delta L, which again was our new equilibrium length, minus Y, where this Y value is going to be wherever we are located between our two amplitudes. We can then, now that we have an equation for our spring force, we would be able to use that when calculating the net force. So here our net force is going to be mass times acceleration, because we have a non-zero value for acceleration when our object is not at equilibrium. So with that, we can plug in our values again. So again, this is using the fact that up is positive and down is negative. That means that our force due to gravity is negative and our spring force is going to be positive. Now we can rearrange this equation. What we saw in the last slide is that K delta L minus mg was equal to 0. This was our forces at the location where we were at our new equilibrium value. If I look at my equation above, I have K delta L minus mg, which I just established was equal to 0 on the previous slide to calculate my delta L value. So what that's going to leave me with is just K times negative Y. So my net force on this box is the exact same as the net force I had on my box horizontally. However, here I have Y instead of X to describe my position. I can change what direction I have being X and Y. We've done this a couple of times in this class. primarily when we were looking at objects on an incline, or when we had two objects and we wanted them to accelerate in the same direction. So instead of calling my vertical direction y, I could call it x. I can say that positive x is downward. I can call it x, I can call it y if I really wanted to, and I loved the letter z, I could use z. We can choose our coordinates. So we can choose what we want to do such that it helps us make sure we understand that the vertical oscillator and the horizontal oscillator behave in the exact same way mathematically. They're the same. The only thing that is different is the fact is that we have a new equilibrium position when we attach our box to the spring. When we do that horizontally, equilibrium is still equilibrium. When we do it vertically, equilibrium has shifted. So again, we don't need to treat horizontal and vertical oscillators differently. Even though gravity is now included, it turns out because gravity both helps and hinders our motion depending on the direction of the object on the spring moving, cancels out. Doesn't matter. It's going to behave the exact same way. So again, I will repeat this as many times as it takes. We can treat vertical and horizontal oscillators the exact same way. And so this is really nice because by using a vertical oscillator, this is a lot easier to visualize. So this is an image from a different textbook. And what we have here is, again, we have a box on a spring, but it's vertical now. And we're going to pretend there's a marker on the other side of this box that is friction-free in contact with paper. And this paper is moving to the left. So what that means is this graph that is included on here, we have our position. Again, in this particular textbook, it's changed y with x. So my position is still considered in the x direction. It also, for reasons I still don't understand why textbooks do this, has positive amplitude as when the box is compressed. It matches, so what it's saying is that up is positive x, down is negative x. Technically left would be positive y, but that's unimportant for this particular example. So we have our positive amplitude, our negative amplitude. In this case, it looks like time has started when we've compressed the spring and as soon as we've let it go and it started moving. So we're following a cosine curve. So our position as a function of time would be cosine omega t, a cosine omega t. We have an amplitude, cosine omega t, where we're probably going to use omega as equal to the square root of k over m. It's probably how we would go through and deal with finding the position at a very particular time. And so with this, we would be able to, as the paper moves, time is changing, so time is increasing as we move to the right based on the paper motion. So we can see how the position changes as a function of time. It's going to trace out the exact same curve we had for the x value. It's just the x value, we had our graph turned 90 degrees to the right. Here, it's in a direction that is drawn such that we can more easily identify sine and cosine because we don't have to spend the 10 seconds to either tilt our head or tilt the graph itself. So let's go ahead and do an example. This is number 21 from the back of the chapter. So what I'd like you to do is pause the video, go through, and try to solve for this particular question. Okay, so for this I'm going to start by drawing my picture. To indicate a ceiling, this is a pretty standard, you just draw little slash lines, that way you know it's a roof and not just a random line. So we're going to have some spring with a rectangular, somehow sealed shut physics textbook, which has a mass of 500 grams or 0.5 kilograms. And we are told that delta L is 20 centimeters or 0.2 meters. So if we didn't have the spring, we would be 20 centimeters different. So we want to find the spring constant, and then we are pulling for part B. I know my spring magically has more coils. That's not physically how that works out. That's just mentally how I can draw. I guess I'll try to make it. I already screwed it up with another part, but well, let's pretend that's the same number of coils. So we are going to be pulling an extra 10 centimeters for part B. We're going to release it, find the period, and then part C, not part copyright, we were going to find the maximum speed value. So these are the 3 points that we really have, and we're going to be able to go through and solve. So for part A, again, we are going to be finding the spring stiffness constant. Well, if we go back to learning about calculating delta L, we saw that delta L was equal to mg divided by k. So we're just going to be able to use that particular equation. In part B, we want to find the period. Well, we know a couple pieces of information about how to calculate period. The equation we've seen before is omega is equal to 2 pi divided by the period. Well, omega is also equal to the square root of k over m. So we're going to be able to use these two equations together to solve for the period. And then to find the maximum speed, well, we've talked about this as just being a omega. So even though in part B we are not using the 10 centimeters, that 10 centimeters is going to act as our amplitude value. Now, for the exams where we're dealing with simple harmonic motion, I will make it explicitly clear if you can keep it in centimeters or have it in SI units. For the textbook, when you have your amplitude in centimeters, again, you're going to be able to keep it in centimeters. On quizzes or exams, I will make it explicitly clear which one I'm looking for. However, for our change in equilibrium and our mass, we do need to convert to SI units in order for our other values to come out in SI units. So it's only the amplitude we can't change. So let's go ahead and let's actually go through and solve this question. So for A, we're going to start with K is equal to mg divided by delta L. So our mass is 0.5 kilograms. G, because we're on Earth, is 9.8 meters per second squared, divided by the change in L, which was given as 20 centimeters, or 0.2 meters. So taking that and plugging it in, when I did this, I ended up getting 24.5 newtons per meter, or because I was given 2 sig figs in this question, 25 newtons per meter. So we're just using the definition of our change in equilibrium to solve for this spring stiffness constant. Now I'm going to set my 2 omega equation, 2 pi over period is equal to square root of k over m to solve for the period. So period is going to be equal to 2 pi times the square root of m divided by k. So this is just rearranging to solve for my period value. So I'm going to have 2 pi times the square root of 0.5 kilograms. When I'm using my k value, I need to make sure I'm using that extra sig fig, so 24.5 newtons per meter. And taking this and plugging it in, I end up getting, sorry, I'm actually doing this the same time I'm doing the lecture. I got 0.897, 598 seconds. Again, I have 2 sig figs, so 0.90 seconds. Because 9 rounds up, it ends up getting to 0.09. So here in B, I need to make sure, and this is a kind of common thing that you'll see in simple harmonic motion, is that the 2 omega equations, or the 3 omega equations, you might have to use multiple of them together to solve for the period or the frequency. So, all right, so let's go ahead and get to part C. So part C is just solving for the maximum speed. So that's going to be our amplitude times omega value. So we had 10 centimeters times the square root of k, so 24.5 newtons per meter divided by the mass of 0.5 kilograms. I never can seem to draw the square root big enough for that. So taking this and plugging it in, I ended up getting exactly 70 centimeters per second, or if we wanted to round this to, or not round this, but put it in SI units, 0.7 meters per second. Again, for exams, I would make it perfectly clear on if you could keep this in centimeters or must have it in meters. All right, so that's going to wrap it up for this first part. Make sure to watch the next part in which we look at the pendulum.